Okay, so from the last video, we had a look at this graph which described, say, the flight of a golf ball from a distance of 0 to a distance of 100 meters, and the graph y-axis is effectively the height of the ball at any particular point. And we were trying to work out, well, what is the rate of change at any particular point on that blue line? And the answer was, I don't know, if we use an average, it doesn't really give us a very good idea. But if we zoom in to the point and then use a teeny tiny distance away from that point as the average, it's going to be at least closer. And then that brought us to this limit theory, where we looked at a gradient as being, well, the standard gradient formula, y2 minus y1 over x2 minus x1, but then said, well, y2, let y2 be just f of x plus h, where h is a tiny distance away from x. So then the formula would be f of x plus h minus f of x over x plus h minus x, and that gets us to this concept here, which is f of x plus h minus f of x over h. And specifically we write it as the limit as h approaches 0. So we say, well, h can be any value, but let's have a look at what happens when h approaches 0. So h becomes more and more negligible, okay, between the 2 points. So how do we apply that to the problem? Well, the problem was that f of x, I'll just show you, well, I'll just write it here, f of x is equal to 2x minus 0.02x squared. Okay, so that's what f of x is. So a little bit like our translations from the previous unit, if I look now at f of x plus h, then all I'm doing is I'm replacing x with x plus h. So that's 2x plus h minus 0.02 x plus h all squared. Okay, now this is, we can simplify this a bit, so let's go. So that's equal to 2x plus 2h minus 0.02 x squared plus 2xh plus h squared. That's just expanding a square. We've got 0.02 out there, so we've got 2x plus 2h minus 0.02x squared plus, what's 0.02 times 2? Hang on, let's have a look. I'm using my calculator on my computer here. 0.02 times 2 is 0.04. 0.04xh plus 0.02h squared. And of course, I made the mistake of not having room my negative numbers properly, so that should be negative and negative there. Okay, so a bit of a long, complicated thing, but let's have a look at it in practice here. So I'm going to substitute f of x and f of x plus h into the formula here. So I'll do that on the next page. So f of x is 2x minus 0.02x squared. So we've got m is equal to f of x plus h. So I should have started off with that. So that's that big long thing there, 2x plus 2h. I'm going to have to keep on flicking through because it's quite long. 2x plus 2h. And then minus 0.02x squared. So minus 0.02x squared. Oops, wrong way. Then I had minus 0.04xh minus 0.04xh. Then I had minus 0.02h squared minus 0.02h squared. Okay. And then I had to subtract f of x. So it's going to be a bit tricky on this line, but I'll just do it underneath here. So f of x was 2x minus 0.02 squared. So we've got minus 2x. And since I'm subtracting negative 0.02, it'll be plus 0.02x squared. So that's the numerator, and the denominator, nice and easy, is just h. And it always is because of what I showed you before. Okay, so that looks a bit scary, but it's not too bad in that the 2x and the minus 2x cancel out. 2x minus 2x is 0. The negative 0.02x squared and the positive 0.02x squared also cancel out. So we're left with 2h minus 0.04 xh minus 0.02 0 to h squared all over h. Okay, I haven't put in the limit thing at the moment because I just want to concentrate on what we're doing here with the gradient. Okay, so that's got a common denominator of h, sorry, a common factor of h at the top there. So that's h outside of 2 minus 0.04x minus h over h. Now remember I said that h is teeny tiny, but it's not equal to 0. So I can cancel out these h's, no dramas at all. They will divide out. And that leaves me with 2 minus 0.04x minus h. Now that's the gradient for a value of h. So what we do now, and this is the bit which sounds a bit tricky, but I'll have to do it on the next line, next page, is we can say the gradient is equal to the limit. This is for the particular point. The limit as h approaches 0 of 2 minus 0.04 to minus 0.04x, whoops, wrong way again, minus h. The limit of that is what the gradient's going to be. Well, as h approaches 0, this is the point where we actually use this gradient, this limit, sorry. So as h approaches 0, what does this approach? Well, it approaches 0 as well. This approaches 0. So what do we have? We have that equaling 2 minus 0.04x. Okay, and this is the gradient formula. This formula will tell us what the gradient is at any point on that graph. Okay, any point on that graph. So if I want to know, let's just say that this point that I have mentioned here, let's just say that's at 25 meters. If I wanted to know what the gradient was at 25 meters, I would simply substitute 25 in for x into my gradient formula, and work it out. So I'm doing this on my calculator. 0.04 times 25 is equal to 1. So that'll be 2 minus 1, which equals 1. So at 25 meters into the flight of the ball is moving at 1 meter across, or 1 meter up in height for every meter across at that point, and that's why we call it an instantaneous rate of change. If I then looked at the gradient at m equals 50, I'll do that on the next page. Sorry, at the distance equals 50. So at 50 meters, I would have the slope as equaling 2 minus 0.04 times 50, and that would be equal to, well, 0.04 times 50 is equal to 2, so it's 2 minus 2. You can use your calculator to work that out, and 2 minus 2 is 0. Okay, so what does that mean? That at 50 meters there is no, well, the gradient is 0, which means that it is traveling 0 meters high for every meter across. So if I look at my graph, it's that point there. It's that point there. Okay, so at 50 meters, the ball has reached a resting point, which we call a turning point, don't we? And then it will start decelerating here. Okay, if I look at 75 meters, what's happening to the ball's rate of change at 75 meters? I can do that too. So at 75 meters, the gradient is 2 minus 0.04 times 75. And again, using my calculator, I can go 0.04 times 75, and I should get 3, yep, which equals -1. There's nothing wrong with a negative gradient. Negative gradient simply means that the graph, that it's going downways instead of upways. Yeah, so it means it's falling by 1 meter for every meter of distance, which kind of makes sense at that point. So there you go. So again, by using limit theories and considering f of x plus h a short distance away from f of x, we can work out the instantaneous rate of change for any function that we're given. I just used a parabola, but you can use the same idea for a line, as well as a cubic, as well as other functions as well, anything that you want to. So after I pause this video, I'm going to give you a straight line, and I'm going to get you to show that when we use the limit theory, the value that we get at the end of the process is the same as the gradient of the straight line, which you should be able to tell from the form that I give it to you in. So have a go at doing that one, and then we'll follow it up in class. That's it.